Okay, specialist maths on reciprocal functions, and we're going to examine how we can sketch these reciprocal functions without the need of a calculator. So let's think first off that reciprocal function is where we have some function of x, the real function of x, in the denominator, and in your numerator is just a 1. So our job is to sketch this unassisted, and the best way to do that is to think about f of x. What is that function? What are the features of f of x, such as x and y intercepts, such as turning points, what is the general shape? Okay, and we're going to draw on our understanding of an f of x function. Could be quadratic, could be linear, could be different type of function, and examine how is that going to then translate into the graph of the reciprocal function. So let's start with this example. Here we go. We have a quadratic, 1 over a quadratic, x squared minus 7x plus 10. And fortunately, this quadratic can be factorized like so. X minus 5 and x minus 2. Good start. So, given that it can be factorized, we are going to now consider a few things. And we're going to use this quadratic f of x as our example, but we're going to generalize the features for all reciprocal functions. So what happens when our f of x is 0? What happens when we get a 0 in our denominator? Well, that's when a function is undefined, and precisely we've got two things happening here. When our f of x, our quadratic, is 0, we end up with x-axis intercepts at x equals 5 and x equals 2. But for the reciprocal function, it's not x-axis intercepts but asymptotes. We've got asymptotic behavior at x equals 5 and at x equals 2. So that means the x-axis intercepts of the f function translates to asymptotes in the reciprocal function. What's the next point? Well, what happens as x increases in value and gets larger and larger and larger? If the y values of f of x increases and get larger and larger and larger, then the reciprocal function y values will decrease and get smaller and smaller and smaller, because they're as it's a fraction, forming a fraction. So for increasing x, we've got, maybe for this function, it has a turning point and then y values increase rapidly, so f of x becomes larger. But the reciprocal function, y decreases to 0. As f of x gets larger, y decreases to 0. So that is in fact asymptotic at y equals 0. Alright, so far what have we achieved? We've realized that we've identified 2 asymptotes here and 1 asymptote there, simply by considering what happens at 2f of x. Alright, what about a third idea about stationary points? So let's think about the stationary point of our f of x. Okay, we can find it by making the derivative is equal to 0, and when we do that, we would realize that it's being a positive parabola, the stationary point is a local minimum. It's a minimum at that point there. So what would happen now to the stationary point for the reciprocal? In fact, what we'll find out shortly when we examine stationary points more carefully, that all minimum turning points of f of x, they become maximum turning points for the reciprocal function. Okay, they swap. And vice versa, if it was a maximum turning point for f of x, then that will be a minimum turning point for the reciprocal function. Another property of reciprocal functions is, alright, let's say for negative values of f of x, alright, when it's less than 0, y is also negative. Okay, so that means if the graph is in the below the x-axis in the negative y quadrant areas, then the reciprocal function will always also be down there. And converse is true. If f of x is positive, the reciprocal function is also positive. So at least we know that the graphs are going to stay in the same half of the Cartesian plane. And the last point that's worth considering is that both graphs f of x and y, the reciprocal function, they both intercept at a particular value. And this is when y is equal to 1. So imagine looking at this function here. When f of x is equal to 1, then we have y is equal to 1 divided by 1, which is 1. Okay, so it allows you to identify a point straight away for the reciprocal function. Okay, and that point exists when f of x is equal to 1. Alright, so we're going to draw on each of these 5 points to help us with sketching our reciprocal function. Alright, so there's our reciprocal function. Let's start to graph it. So first thing for us to consider was point 1. Point 1 was when f of x is 0. So when f of x is 0, and this is useful to consider when it's in here, turning point form, we're going to get x-intercepts when f of x is 0. And it's important to identify them when x is 2 and when x is 5. There's x equals 2, 3, 4, 5, and that's when x equals 5. So they're going to be turning points of our parabola. And what are they for the reciprocal function? They are asymptotes. So let's put them in. I'm going to grab, we'll do it like this, for it to be asymptotic. Draw in asymptotes. Oop. Well, let me just put this to the very back. And bring backwards. Where's my asymptotes? I can't seem to draw bloody asymptotes. Here we go. Reorder. Top layer. There we go. Alright, I lost him for a second. Okay, so there's one. And the second asymptote. And on the graph it's important to label these asymptotes. X equals to 5 and x equals to 2. Alright. Next step is the turning point. So the turning point is occurs when the derivative of the f of x function is equal to 0, and we get 2x minus 7 equals 0. So x equals 7 halves. So x equals 7 halves is 3.5. 1, 2, 3, and 0.5. So it's right there. As you can see, that is precisely halfway in between the two x-intercepts, the two asymptotes as well. So I'm going to substitute the x value into my f of x function, and I'm going to get that as my turning point of the parabola. Now just keep in mind, this is just our parabola here, x squared minus 7x plus 10, and I'm going to lightly sketch that one. So 3.5 and negative 9/4. That is 2.25 negative. So 1, 2, about there and a little bit more. So I think about there is my turning point. Now, let's see how this works. It's going to come up like that. That looks parabolic to me. And this side, whoa, getting rough. Yeah, okay, now we're talking. So roughly that is our parabola. Now that's a good starting point to put in. Okay, because once we've drawn in the parabola, then it gives us a like a beginning point, like a foundation to be able to draw this reciprocal function. Now, some important things to consider when we're sketching a reciprocal function is that for any x and y point on f of x, such as the turning point here, given by that coordinate, then that the corresponding point on the reciprocal function is 1 over y. So we just take the reciprocal of the y value. So taking the reciprocal of this value here allows me to find a coordinate for the reciprocal function. So 4 over 9 is less than 1, and it's negative less than 1. It's about there. Okay, so that is now going to be a point on my reciprocal function. These are asymptotes for the reciprocal function. Alright, we're starting to get some information so to be able to sketch this. Now, another point to think about is at the x-intercepts, I have my asymptotes, which I've got there. Alright, now, next point, as x goes to infinity, the f of x also goes to infinity, and we can see that on the parabola. So as x increases, the y coordinate of the parabola increases. But for the reciprocal function, that's going to make the reciprocal function y go down to 0. So that means we've got another asymptote. Sketch the asymptote here, y equals 0. So asymptotic y equals 0 also. Reorder top layer. Okay. So the graph is going to be asymptotic vertically here and asymptotic horizontally here. Now that we can start to imagine things coming down like this, doing a bit of that, and then asymptotic again like this, and same on this side, running along this asymptote, doing a little bit of that, and then running up vertically. Okay, and you'll also see that the reciprocal function will look a little bit like that. Ooh, turn there and then down. But let's get some more information before we plug along and start sketching this thing. Alright, this is an important thing to consider. Let's plot the intersection point. So this is the point where the reciprocal function intersects the parabola. So we are solving x squared minus 7x plus 10 is equal to 1 for x. And when done by hand, we have to do this by completing the square. Okay, so completing the square means taking the first two parts of x here, that bit, and solve that and carry out the completing the square procedure for that. Okay, so completing the square, in order to find this common point when y is 1, we set up the equation f of x is equal to 1, then complete completing the square of the first two terms allows a perfect square here. Then we subtract half of the coefficient of x squared, so 7 over 2 squared gives us that. And then taking one to the other side gives positive 9. 9 with a common denominator of 4 is 36 over 4. And we simplify this down, square root both sides, and then add 7 halves to the other side, and we get this number in third form, approximately this. X is 5.3 or 7 or 1.7. So I'm going to approximately put these points on our graph. So 1, 2, 3, 4, 5, and a little bit. So that there, and 5.3 and 1.7. About there. So we'll have the two common points that our graphs will share are intersecting here. This is where the reciprocal and the parabola are going to intercept. There and there. Okay, so this point doesn't necessarily need to be labeled with a coordinate, but it is probably useful to set up some kind of structure to be able to sketch accurately. Okay, so having found those points, one other important thing is determine the turning point of our reciprocal function. And we've got that point right there as the turning point of the reciprocal function. We obtained that by through the idea of if I know the turning point of f of x, which is this point here, then I take the reciprocal of the y coordinate, just this one. That's a common point on the reciprocal function, that one. Okay, so let's start to sketch this. I'm going to do it in blue. So we've got it along here, it is asymptotic. And then it's going to come down, start to pull away, and it's going to intercept here, turn a bit, and then become asymptotic again, running along here. Whoop. Okay, same on this side. It's going to only be asymptotic, run down, whoop, bit too hard, pass through that point where y is 1, and whoop, running along here. Oh, terrible. This is why it needs to be done in pencil whenever you do a sketch in an exam, particularly drawing a sketch along an asymptote. You've got to be careful not to cross. If your graph crosses an asymptote on an exam, then you will lose marks. So you have to carefully sketch the graph running closer and closer to the asymptote, but never touching and never passing through it. Alright. Now, how does the graph look lastly? Okay. Now, one thing I need to keep in mind is that here, as f of x is negative, then y, the reciprocal function, is also negative. So drawing on that idea, that means here the parabola is negative, my reciprocal function is going to be negative also. It's asymptotic at these points, so I'm going to have it run along the asymptote, and then it's going to turn there, down, and become asymptotic again, like so. And there we have it. Our reciprocal function is in blue. Y. It's graph y. Now, what you need to do finally, the very last step, particularly in an exam situation, is grab your rubber and rub out your parabola. We use that parabola to help find the turning point where it needs to be and a common point where the two graphs are going to intercept. But unless the question stipulates directly that you need that f of x function, you need to rub it out at the end. So that's our reciprocal function. Fair enough.